Okay, let's dive into some of the more syntactic side of Rust and still some of the basics, I think. So let's very quickly have a look at how you create functions. So I think we saw this earlier, but let's dig into a little bit more detail. I'm just going to work in the main.rs here. So to define a new function, we use the keyword fn. We give it a name. I know earlier we used it greet or something, but maybe we have a function called sum or add, something like that. Add is maybe going to add two integers. So we have an a integer of type u32 and b of type u32. Okay, so already this may look a little bit strange. You may, and it's just Rust being quite explicit about its underlying low-level nature popping through. So in another language, you might have said, well, A is of type int and B is of type int. These are absolutely type int, but we're being very explicit that this is an unsigned 32-bit int. So Rust has got like really nice comprehensive types. There are, I think you could have an unsigned 16-bit int. I think there would be an unsigned 8-bit int as well. There's, of course, a signed version of everything. So let's see if there's an unsigned 64. There is an unsigned 128. That's a really large unsigned int. I don't think there's a 256, but maybe I'm wrong. No, so I think it goes up to unsigned 128. You have the signed versions as well. So signed and unsigned means that the integer could be negative or not. Unsigned means it can't be negative. Signed means it can be negative. So you have I8, all I16, I32, I64, and I128 as well for all the signed integers. So an I version of an int is a signed version. So probably our add function actually should take signed integers. Let's do that. And our function is going to return. So I could just open scope right here. If I like and save, this will probably compile because effectively what add is now, add is a function that takes two ints but returns nothing, if that makes sense. And actually the Rust extension is formatting my code to do this, sometimes a little irritatingly, but let's actually make this thing return the answer a plus b. You can be explicit about using the word return. That is okay. I see there's a warning here. And mismatch types, expected open close brackets, found I32. So what does this mean? Well, this is saying that your function is clearly returning an I32. It has found that you are returning an I32, but I expected you to be returning an open close bracket. So what is an open close bracket? Open close bracket is this. It is actually a type as well in Rust. And if you've used so maybe newer languages like Haskell certainly does this, and others, you may know of a type called unit. I think Scala, for example, has the unit type inside it. In Rust, the unit type is written like this, open close bracket, and that means it's effectively like an empty tuple, if that sort of makes sense. I suppose that's a good way to think about it. It's like an empty tuple. So this is telling you that Rust functions, if you're not explicit about what the return type is, Rust will default it to the empty tuple. So this function returns an empty tuple. And if I do nothing in the function, that's totally fine. So your function is allowed to return nothing, and i.e. do nothing. That's fine. But when we earlier said we return actually an integer, an I32, that type is incorrect. So we need to be specific that we return an I32 as well, right? So there's just our compiler moaning at us. Good practice in Rust is to not use the return keyword as much as possible. And your last statement, which does not include a semicolon, is automatically the thing that is returned. So you can leave out the keyword return, and as long as you have no semicolon at the end of that line, that is the value returned. If that makes sense, but you can of course also write return and the semicolon if you like. It's just not idiomatic Rust, I suppose. So good to know that this open close bracket is the unit type. Maybe in other languages you might call this the void type, but that's actually a bad word. It's really not. In the mathematical sense, the unit type is not the same as void. Void is just a badly named unit in other languages. So you start using the word unit. There we go. So there's our function add, and it returns an I32. So it's actually really simple. That's how simply you can declare a function. In order to call that function, we sort of saw this earlier. It's really simple. You can just go add 5, 10 or whatever. That'll call the function. Great. There we go. We're not assigning the result to anything. If we wanted to, we can use the word let to create a variable, and I can say x equals that thing. So I'm naming a variable. X equals add. Later on, if I would like to reassign x to something else, 10, 20 maybe, I can't do that, and it's because let by default creates an immutable variable, or value I should say. So x is immutable at this point, and so I'm getting a warning saying cannot assign twice to immutable variable x. So that's great. So by default, variables are immutable. I can of course make them mutable, and I just have to add the sort of keyword mut in front of it to say x is a mutable I32. And you will see that when I hover over x, you will see almost the mut is kind of in the type system there, so you can kind of see it there. I'm trying to think how we could, of course here A and I, these A's and B's are also immutable. So A and B here are also immutable I32. So I couldn't reassign them here. It would be weird if I did anyway, but I certainly couldn't here. And it will say kind of the same thing. Cannot assign to immutable argument A. I can though create a mutable argument if I like. This is like a strange thing to do, but I suppose in some languages you would want to do this. Pass in the kind of output variable or something. And say I wanted to do that with C, and I want to set C to 10 before I return this thing. I think I would just go. Strangely, it's like, maybe it's not compiled. I don't know why I'm not getting a warning. Oh, yeah, I'm not getting a warning because I'm not passing it up here. So let's just comment that out for now because we don't know how to call it yet. Yes, okay, here's our error again. We can't do it. So I think we can say that C is mutable by putting that there. It's just saying if this is intentional. So unused. So C is unused for now. That's interesting. So it is mutable, but of course, is it going to mutate it when it gets passed in? I don't think so, because I think it's going to be a copy. So let's try. So we'll go let mut C equals 10, and we're going to add 10 and C, and let's see how that works. So C is being passed in as a mutable variable there, and this is just some interesting. It says actually it doesn't need to be mutable, and it's because it's not really a reference. So even though it gets mutated, you get passed in there as a mut C. It's like I could, I suppose, assign it twice or something. Assigned to, but it's never used. Yes, of course, because let's add it there as well. And does this? Is never read. Okay, yeah, totally. It's like it's not read equals C plus 10. I'm just following the compiler errors here and trying to help it along. Value assigned to C is never read. Is it? Because C equals C plus 10. I don't know. I mean, it's weird and wonderful, but you can of course use this keyword mut here in front of parameters as well if you want them to be truly mutable. Often, passing an int as a parameter here, it's only really in scope of this thing. It's not going to be passed as a reference back to this original C up here. There are other ways to do that. So we could be, and the way you would do that is like, I want a mutable reference to C because I want to change it. And then I would fall more into this like C style approach where I want a reference to in I32. And I would like that to be a mutable reference, I guess. And then if I assign something to it, I think I would go like this. I would dereference it, and I would set 40 to the thing that C points to, if that makes sense. And so here now, Here now, what is happening when I pass the I32, I need to pass a reference to it. And that's good. Cannot assign to that, which is behind a reference. C is a thing, so the data it refers to cannot be written. Yes, I think this needs to be a reference to a mutable I32, something like this. And this probably, I think I need to make this a mut up there as well, and probably say that I'm passing a mutable reference to C there. So there are ways to fiddle your way through this of passing references to values so that they can be changed by functions. And you just have to go through this, you've got to understand the referencing and adding the mutability flag to those references as well. So you kind of know explicitly when you're designing a function or calling a function what that function is going to do to your stuff, if that makes sense. So this, from a C perspective, that was never really clear. C, you could be passed pointers to things. Your function could take a pointer to something. You didn't know when you called that function whether it was going to write back to that pointer or whether it was just going to read from it. Rust has done a great job of adding this mutability flag into the type system so that it is clear what is happening, and it'll track it through. So I think this is kind of generally junk anyway, but that was a little bit deeper than I wanted to go. Anyway, so we just wanted to show how declaring a function works. Let's just fix this again, say vertical. Let's see, what else? Macros. Okay, so just very quickly, I'm not going to show you how to build a macro, but wherever you see these functions which have exclamation marks at the back, that is Rust invoking a macro. So I can actually control click often through to these things, and I can see that this is a macro. So info, it's not really a function. It looks like a function, but actually underneath it's the compiler is generating code underneath this macro, which is useful in many, many ways, possibly for a logging type of library. At some point when you compile for release mode, maybe you want to compile those log statements out of your code. In fact, you want them all stripped. And so having a macro during compilation that is stripping out the code to do that is very useful. And you see these macros fairly often. Even the regular print function is a macro. Format we saw earlier is another macro for kind of joining strings together. Those are all macros. You can define your own macros. They're a little complicated to define, but just so that you know, whenever you see this exclamation mark, that is a Rust macro being invoked. And a little different to a function. In fact, there could be multiple functions being invoked underneath a macro. A macro generates code effectively. So just know them. We talked about unit as well. Okay, another important part of the Rust syntax is talking about structures. Like, how do I create data types? And there's two ways to do it. You can use structs or you can use enums, and both of them are very powerful. So we can define a new struct. You just literally say struct. We give it a name like a dog or something, and then you just add fields into that struct. So you could say, well, a dog has got a name, which is a string, and he has an age, which is an unsigned 8. Probably a good choice for a dog's age. I don't think dogs could ever be older than 256 years. So there we go. We're making use of a low-level unsigned U8 type for our dog, and then we can make use of that dog. We can create one. Let my dog equal dog. We can create it, and the way we create that dog is we just use kind of the same syntax. We say name is Rex, and this we have to go to string. We saw that earlier, and the age is 10 of this dog. So that's how we can create. And I just pressed save there. The extension formatted my code for me, but now we have a my dog, which is a dog with these fields. So you just kind of use this sort of syntax, very simple syntax, for creating a structure. So that's a struct. These structs can of course be nested, all that sort of thing. Very much a regular struct. You also have another nice piece is enums. Enums are, I suppose, an alternate type of structure where you've got choice in the structure. So you could say enum an animal is either a dog, or a cat, for example. There's a basic enum. And so now I could say, let my pet equal a dog. I think I have to go animal dog. I have to prefix it with its enum type and then the specific type underneath. So now my pet is an animal, but its specific type is a dog inside that enum, right? The very cool thing, and this will be different from C# or Java, where you have just very simple enums. These enums in Rust can be more complex. So you can say for a dog has also a, so I could just copy above, I could say it has a string as its name and it has a U8 as its age, which is fine. So now when you construct a dog, you must also specify a string and a U8 to be tagged along, which could be different to a cat, because maybe a cat has a string as its name and it has a, how would a cat be different to a dog? I don't know. Maybe it has another string which is like its subtype or something, and then it has a U8 as its age. So cats and dogs could have different ways of constructing them. They carry around different data with them, if that makes sense. And so now when I wonder if this is just compiling. I don't think so. Yes, okay, so when we're constructing it, we can pass those things. So if I'm specifically a dog and I am age 10, I would construct it like that. So my pet is an animal. I think earlier I wasn't, so if I take this out, this is quite interesting. Look, the type of my pet becomes a function, like a dog constructing function, my pet. So that's a bit wild, yeah, because you can see, like, if I pass a dog, I'll produce an animal. So there's a little bit of functional stuff dangling through there. So, but we want it to be of type animal, right? We know that my pet is an animal, and dog requires those things. If I take that out now and I save, it will say mismatched. I'm expecting you to be an animal, but you're giving me like a function which takes some strings and gives me an animal, which would obviously be wrong. So that's how we construct a dog, and my pet2 is maybe a cat, animal cat, and cat has a name. What is a good name for a cat? Garfield, string, and he is green cat, and he is 20 years old, because cats can live longer than dogs, I think. There we go. So make that a little smaller. So you can see specifically that dogs and cats are constructed in different ways. And the cool thing is the enum was quite explicit about that. So those are enums, very powerful way of creating alternative data types that are still the same type, if that makes sense. They're both animals, but they're constructed in different ways. And that's done very, very smoothly. These are called discriminated unions, or sum types. Very quickly, what are classes and what are traits? So let's quickly see how we could very simply sort of implement an object-oriented approach, because you're saying we've got structs and we've got enums, great, but how do I do like an OO? How do I add a bark function to this dog? And in Rust, it doesn't use a class keyword like you would expect in .NET or Java. Or C++ or whatever. The way we do this is we can literally implement the dog struct, and we can add functions to it. So we can say, so effectively classes are just structs that have functions attached to them, if that makes sense. So now we can add a bark function. Yeah, bark function makes sense for a dog. And then it's very similar to Python in that we provide a self-reference, like a reference to the dog itself comes through into the function. So that's how you bring it into scope. Bark maybe returns a string, and then we can say like format. We want something barked, and we want like self.name barked, maybe, something like that. So that's by by saying we bark, the bark function receives a reference to itself. This is almost like the this pointer, right? And I wonder if we could even rename it to this. I don't think we can. I think we have to specifically name it self. There's obviously a reason we have to call it self. Very much like Python, I suppose. So Python also takes the reference to itself as its first argument in an object method. Yeah. So that's how we would implement that. So now this means that my dog up here, our earlier dog, has now a bark function associated with it. And so that's how you do it effectively. So let's move the little animal out of the way here. But that's how you then build object-oriented approach to things. You create a struct, and then you create an implementation of that struct where you can attach whatever you like to that struct. And of course you can have things like these are public and these are not public. So age actually in this struct is not public, whereas that one is public. This one could be public as well. So you've got this kind of public-private modifiers as well. I think because everything is defined in this main thing, everything is visible for now, and that's fine. You can, I believe, even implement an enum. Let's try. So let's implement animal, and maybe on this we want to go function eat or something. We want an eat function. And it returns a string, and it goes, I'm just going to copy this, and we say this guy ate. And interestingly here, like we don't, because keeping in mind animal is this type, it doesn't actually have a name, it's not the same as that type, it doesn't have a name or anything. It has to get itself from, it needs to get its name from this first parameter. If it's the dog, it's the first one. If it's the cat, it's also the first one. That's cool. So we have to somehow get access to that thing. So how do we destructure these types, I suppose, is the point. So the way we can do that is we use pattern matching. So we would say match on self. And we would say, well, if we are a dog, I want the name and the age. And I think I go like this. Is it? I can't remember the exact syntax, but let's try. So he ate. Like that, and I think I go comma. And if I'm a dog, I'm a cat, sorry, I have a name and a color or something, and an age. It's weird that I would have a color, but I'm fine with it. It's not happy with this. Expected tuple struct or tuple variant found struct dog. Oh, sorry, yes, I'm actually trying to destructure an animal. Sorry, it's getting confused because I have another struct called dog, which is wrong. Oh, fat arrow. Okay, so we need a... And look how the compiler is helping me along there, which is really cool. Like on that arrow, it was saying try using a fat arrow. The fat arrow is an equals arrow, and it's going format. Maybe I should get rid of this one. Format 8. Yeah, there we go. So that is how I destructure an enum into its component. So using pattern matching. So you say match of that type, and then it's like if it's this type, then I just effectively name those fields. I want to pull the values out into these named fields called name, age, color, age. And here there's a little warning saying I'm not using age, so I could just have underscored these things that I'm not using because I don't care about them. I'm only grabbing the name out. Does that make sense? So that is pattern matching on an animal. So now I can go my pet dot eat now. And it doesn't matter what kind it is, whether it's a dog or a cat, it will, so I could just say here, the dog. So this would say Rex, the dog ate, and this would be Garfield, the cat ate. And so there I've got like some sort of like polymorphism, I suppose, happening in an enumerated data type. So that's super cool, super cool. So that's classes. We also talked about classes, and we also talked about pattern matching. So that's nice, in some way. Yeah. Okay. The last thing is traits. Now traits are a completely different way of achieving a sort of object-oriented feel for things without having to create these objects, I suppose. So what we could do is I wonder if I should just delete all of this because it will create some confusion. I'm going to delete it all. What we could do is we could say, hey, you know what, like I want to implement, I'll kill this as well. I want to implement bark functionality. So I want a function which is bark, and this function can take kind of anything. It can take any kind of animal, as long as that animal has some sort of animal trait about it. I will support it. So it's any, and so let's see what the animal trait looks like. So then we can define something called the trait of type animal. It's a trait called animal, sorry, and within this trait I'm going to have a bark. I'll have maybe a name function or something, and we'll take a self, and this thing must return a string. So it's like effectively I'm creating a trait which is almost like some kind of implementable method. So anything which has a animal trait must have a function called name on it, which returns a string. That's effectively what trait means. I'm not attaching it to any specific object yet. I'm just saying there is out there a trait that animal type things have got name functions on them. And then I can create a function called bark, which can take one of anything that has this trait on it, and I can make use of it. I think I've got a compile issue here because I need to say the word implement. So bark takes any old thing. As long as it implements the animal trait, I can give you a string. And so let's just try this. So we'd say format, and maybe here we'd say barked. And this would be the animal.name. So we want to get the animal's name and we want to have it bark, no matter what it is, right? So that seems interesting. So how do you use this then? So now you're saying any type can be an animal as long as it implements this name. So what could that type be? Well, I suppose we could have a struct. Let's have a few examples. We could have a struct cat, and maybe a struct cat has got, I don't want to just put a name in there, but maybe he has a birth name or something, which is a string. So a cat has got that. And then we can implement, and so we're not implementing a name functions there. Anywhere else we can go, well, let's implement animal for cat here. And then we literally implement it. We say, actually I can save here and I can have this thing generate the code for me, implement the missing members. And so somewhere else I can go and implement that cat is an animal by implementing its little name function. And so here I might say, format, like, well, what is this cat's name? He only has a birth name. We could say a cat who was born with name something, and then it's self.birth name, right? So we haven't gone and fiddled with cat. We haven't made cat itself implement animal inside it. It's got its own implementation, which is very different. Implement of cat, maybe cats do other things, function meow or whatever. Maybe cats can meow and format cat meowed. There we go. So cats have got their own implementations. However, somewhere else you can go and say, oh, they're also animals, because here's how they behave like an animal. Meaning that I can create a bark function for any old animal, and I can go and find that implementation here. And so maybe this seems a little complicated because you'd say, well, why wouldn't I just implement it directly inside cat? Totally fine, of course you can. However, there's some other magical properties of this. So let's just use it first. So we'll create a new cat. My pet is a cat, and his birth name was Robert. ToString, cool. So we've got a cool cat now. Yeah, we've got a pet, and he can also, can he bark? Well, we can, because we can call the function down here. It's actually not on him, but we can just call it bark my pet, which should be fine because bark says, yes, your pet does implement the animal thing, so I'm going to call that name function inside him. Interestingly though, you could have other stuff. You could say, well, bark, what if I have like an x is some random string, right? I could also bark this X, right? Well, I could say, well, you know what, like I want strings to just be animals as well. And so how can I do that? Well, I can say, well, I want to implement animal for string. A string who is not an animal. You know, strings maybe don't have names, but there I've implemented animal for string, and now I've attached this name function, and I can bark with a string. I could also even bark with like a number or something. So I could implement animal for U32, and I could say an int who is not an animal. And now the compiler is happy that I can bark with an int, I could bark with a string, I could also bark with an actual animal, and that's fine. And so that's what traits are all about. Traits are like this alternate way of doing fairly object-oriented stuff, but without using OO. It's effectively just like coercing types into the right type, so providing implementations for functions, if that makes sense. And this is an alternate approach to classes, I suppose. Quite often these can be called type classes. In other languages you might call these type classes. Yeah. So those are traits in Rust. So you can see there's many paradigms that you can design software.